হ্যালো ভিউয়ার্স, ওয়েলকাম টু দ্য চ্যানেল ডিপিসি স্মার্ট চ্যানেলে আপনাদের সবাইকে স্বাগত জানাচ্ছি। ইন টুডেজ ভিডিও I will discuss about a topic that is simple harmonic motion and oscillation under undergraduate BTech Knockout Physics syllabus of module mechanics. Theory part of this undergraduate BTech Knockout syllabus will be discussed in this channel. For numerical problems and previous year numerical problems and their solutions, you may join my online classes. To join my online classes, you may contact me through the WhatsApp number given in the screen, and also you can directly message me through Instagram and Facebook. In future, the numerical problem and their solutions will also be available on YouTube. But for that, you have to join the channel, and for that, do subscribe my channel. So without wasting time, let us enter the classroom. So this is the first module of undergraduate BTech Physics syllabus under Knockout. The paper code name is PH101 and 201. In today's class, I will discuss the harmonic oscillator and simple harmonic oscillator, different type of oscillators, simple harmonic motion, that is the acoustic part of this mechanics syllabus. Now, when does a particle vibrate? A particle will vibrate if it is displaced from its initial rest position and a force starts acting on that particle and tries to bring back the particle to its original position or initial positions. Then the particle starts vibrating. Now another term is there which is called restoring force or force of restitution. Now whenever a particle is displaced from its initial position or rest position, the force starts acting on that particle which tries to bring back the particle to its rest position. Now this that force which starts acting on the particle and tries to bring back to initial position of rest is called force of restitution or restoring force. Now the general form of the restoring force is, it is a function of displacement. So restoring force is a function of displacement. So function of x, and we can express the general form of the restoring force as in a polynomial form, that is a0 plus a1x plus a2x square a3x cube and so on, where x is displacement. And a0, a1, a2 and a0, a1, a2 all are constants. Now when x equals to 0, that means displacement is 0, restoring force is 0 as it is function of x. Also when that means if we put the value here, it will be 0 equals to a0 plus 0, or therefore a0 ta পাওয়া যাবে কি a0 equals to 0. So এখানে a0 টার্মটা we will put a0 as 0. Again, when displacement is very small, so we can, for that case, we can neglect the higher terms of this displacement, that is x square, x cube and so on. So all higher terms becomes negligible. So in that case, we can write the restoring force Fx equals to A1 into x, where this A1 constant is, we can write, that is minus of k, as the restoring force tries, the direction of the restoring force is opposite to the direction of the displacement. So as the restoring force is tries to bring back the position to its rest position or initial position, that's why we can put the coefficient A1 equals to a constant minus k. So finally we get finally the restoring force Fx equals to minus of k into x. Next, we will discuss about the simple harmonic motion and simple harmonic oscillation. Simple harmonic motion is a type of vibration where there are few conditions that should be satisfied by the particle which is vibrating. That is, conditions are, first condition should be the particle exhibits a periodic motion. Second condition is displacement is very small. Third condition is the restoring force is directly proportional to the displacement and oppositely directed towards the displacement. So if the vibration which satisfies these three conditions, then the particle can be said it is exhibiting a simple harmonic motion. Now, what do you mean by simple harmonic oscillator? An simple harmonic oscillator is an oscillating system which exhibits simple harmonic motion, that is called simple harmonic oscillator. That means an oscillating system obeying these three conditions, that means exhibiting or executing a periodic motion, secondly displacement is very small, and thirdly the restoring force of this particle or a oscillating system, restoring force is directly proportional to and oppositely directed to the displacement. So if an oscillating system exhibits these three properties or exhibits a simple harmonic motion, then that system is called simple harmonic oscillator. Now there are two types of simple harmonic motion, that is, one is linear harmonic motion and second one is angular harmonic motion. Now firstly we will start with linear simple harmonic motion or motion under linear restoring force. That is linear simple harmonic motion or motion under linear restoring force. So now we will find out the differential equation of motion for a linear simple harmonic motion or a motion of a particle under linear restoring force. Now suppose x is the displacement. So according to the SHO or simple harmonic motion, the force is minus of k into x. Now force we can write as m d2x dt2 and m into acceleration, that is equals to minus of k into x, where or d2x dt2 that would be equals to minus k by m into x, or we can write k by m as omega square x, where omega equals to root under of k by m. Or the differential equation would be d2x dt2 plus omega square x equals to 0. So this is the differential equation for linear simple harmonic motion, where omega is the frequency of the motion, which is equals to root under k by m, and time period would be 2 pi by omega, that would be 2 pi into root over m by k. So this is the differential equation. Differential equation for linear SHM, simple harmonic motion. Now we have to solve the differential equation. So solution of this differential equation. Now for that, let us take x equals to a e to the power m into t is the solution of this solution for x. So if we put this in equation here, we will get m square a e to the power m into t plus omega square a e to the power mt, that is equals to 0, or a e to the power mt common করে থাকবে কি omega square plus m square equals to 0, or m would be plus minus I into omega. So we get value of m plus minus I omega. Where I equals to root under minus 1. Now what would be these are the two solutions of m. So in that case, we know that solution would be x equals to a1 e to the power I omega t plus b1 e to the power minus of I omega t. Now we can expand e to the power I omega t and e to the power minus I omega t in the form of cosine and sine form. So we can write a1 into cos omega t plus I sine omega t plus b1 into cos omega t minus of I sine omega t. So if we take common cosine term together and sine term together, we will get a1 plus b1 into cos of omega t plus I into a1 minus b1 sin of omega t. Now let us take this a1 plus b1 and I into a1 minus b1 as a1 plus b1. Let us take a sin phi and I into a1 minus b1. Let us take a cosine phi. So x would be then a sin phi cos omega t plus a cos phi sin of omega t. So it would be a into sin of omega t plus phi. Here I have taken a1 plus b1 equals to a sin phi. You can also take a cos phi here. Similarly, this term I have taken a cos phi. You can also here you can take this as a sin phi. So this, in that case, it would be x equals to a into cos of omega t plus phi. So both this and this both are the solutions of x. So finally we get the displacement of particle exhibiting linear simple harmonic motion as x equals to a sin of omega t plus phi or a cos of omega t plus phi. So this is the solution for simple harmonic for the differential equation of linear simple harmonic motion. Next another type of simple harmonic motion is also present, that is called the angular simple harmonic motion. Angular movement is present here and the displacement is measured in terms of angular displacement. For example, a string mass oscillating system. That means a disc hanging from a rigid support and it is twisted. So it will execute angular simple harmonic motion. For that case also we have to determine the solution of the angular simple harmonic motion. So here what are the three conditions that should be satisfied by the system? That is, the motion would be periodic. Secondly, restoring force which is denoted as tau here, that would be proportional to angular displacement theta. So the restoring force would be proportional to angular displacement theta. and the displacement would be oppositely directed to the restoring force. So here the restoring force would be minus of theta, or tau equals to some constant c into theta. The tau restoring force is also equal to the moment of inertia of the system I into, and that is called angular acceleration, where I is the, so tau equals to I into alpha, that I is the moment of inertia, and alpha is angular acceleration, that is d2 theta by dt2, that is called angular acceleration. It would be I into d2 theta by dt2. Now from this equation we get I into d2 theta by dt2 equals to minus of c theta. So this is the differential equation of angular simple harmonic motion. Now one thing I want to mention, that for linear simple harmonic motion, this is the differential equation, and the solution of the differential equation we obtain, that is x equals to a sin omega t plus phi and a cos omega t plus phi. But we can also write the general solution of x as these two are also valid, that is x, we can write x equals to a sin omega t plus phi or a cos omega t plus phi. But in general term, there are other form of this solution which we can write as, another form is, we can also write that is a into cos of omega t plus b sin of omega t. This is another form. Third form we can write as complex form, that is c e to the power j omega t plus c star complex conjugate e to the power minus of j omega t. This is also the solution of x. These are different forms of solutions of x. Another we can write as, we can also write that is real part of c e to the power j omega t. This is also a form. And similarly real part of c e to the power minus of j omega t. So what I am trying to say, that all these are solution x, but these are of different forms. So according to the situation or according to the problem, we can use all these forms of or solutions of x. Now one term I want to discuss about, or I want to let you know, that what do you mean by word epoch in acoustics. What is epoch? For any kind of wave, the initial phase is called the epoch. That means for the initial phase of any wave is called epoch. That means if we write the displacement as x equals to a sin of omega t plus phi, here phi is called the initial phase or epoch. Next I will discuss about the energy of simple harmonic motion. So the magnitude of the force acting on simple harmonic motion, that is k into x, that is we have taken the magnitude. So force, the potential energy of SHM, that we can write as integration 0 to x f dx or integration 0 to x work done by the force, that is integration 0 to x kx dx, that would be half of kx square. That is the potential energy. Now kinetic energy would be half of mx dot square, where x equals to a sin of omega t plus phi. That means x dot, that is velocity, would be a omega cos of omega t plus phi. So here if we put it, half m square omega square cos square of omega t plus phi is the kinetic energy, and potential energy is half kx square, that means half of k into square sin square omega t plus phi. So we have put a value of x in both the cases, kinetic and potential energy. So now for total energy would be E, that would be potential energy E plus kinetic energy. So that would be half k square sin square omega t plus phi plus half m square omega square into cos square omega t plus phi. Now for the in case of the differential equation of linear simple harmonic motion, we got that k by m, root under k by m, that is equals to omega, or k would be omega square m. If we put it the value of k here, we will get E would be half of m square omega square sin square of omega t plus phi plus half m square omega square into cos square omega t plus phi. So total would be, if we take common half m square omega square, in bracket it would be sin square term plus cos square term, which is equals to 1. Cos square term. The total energy would be E half m square omega square, which is equals to constant. So total energy for kinetic for total energy, that is kinetic and potential energy summation, that is constant. So it came as a question in a semester in previous year. So this is the answer, how we can prove it. And also we may be asked to draw the energy versus phase, diagram for this simple harmonic motion or simple harmonic oscillator. So for that case, you can draw like this. So this is energy E, maybe kinetic or potential, or kinetic energy in along y direction, and along x direction it would be phase, that is omega t plus phi. So if we plot this, it will be like this. So if we plot E along y axis and omega t plus phi along x axis, for kinetic energy graph, this would be, that is the plot of kinetic energy, and this one is the plot of potential energy. So whenever kinetic energy is maximum, potential energy becomes minimum. Inversely, when potential energy is maximum, kinetic energy becomes minimum. So as a result of that, total energy becomes constant. And this is for ideal case. Ideal case, in case of simple harmonic motion, the total energy is constant. So this is the end of this video, or end of this class, today's class. See you in the next video. Do subscribe my channel. Till then, bye.